In this video, we're going to talk about shock waves in traffic streams. The analysis of shock waves in traffic streams allows the study of backups and queuing on a highway due to a sudden reduction in capacity. When the reduction in capacity on a segment of a highway creates congestion that propagates along the highway, we have what is known as a bottleneck condition. The sudden capacity reduction could be because of accidents, reduction in the number of lanes, work zones, a signal turning red, a slow track or several slow tracks on steep grades, etc. Whatever the reason, at some location on a highway there is a sudden change in the flow state which results in moving queues, which I would typically refer to as platoons that grow and shrink in time. To visualize the shock wave phenomenon, consider a situation with relatively light traffic. Under these conditions, the flow and density are representative of the traffic demand and there is freedom to maneuver. That is, these conditions represent uncongested conditions. Now, suppose there is an accident that blocks 2 of the 3 lanes. Because of the accident, several different traffic states are created. The vehicles passing the scene of the accident can flow at most at the capacity of the one lane that is left. This state is shown in orange in this graph. This is a state passing the scene of the accident. If the demand of the 3 lanes upstream of the accident is greater than the single lane capacity of the accident, a congested state will form upstream of the accident. This state is shown in red. Notice that there is a stationary, not moving interface between these 2 states. This is represented by this green line. This is the interface between the orange and the red state. Upstream of this congested state, vehicles are still approaching the scene of the accident unaffected by the conditions downstream. This is represented by this blue color. Between the approach and congested state and the congested state, there is another interface that in this example would be moving upstream. This is represented by this red line. Finally, there is one more interface between the conditions on the accident location, represented by the orange, the one through which the traffic is flowing, and the downstream conditions. That is another stationary interface represented by this orange line here. Note that the conditions downstream is in general different from the approach conditions. So the conditions over here and over here are typically different. The phenomenon of an interface between different flow states is usually referred to as a shock wave in the traffic stream. A shock wave exists whenever traffic streams of varying stream conditions, different flow, density, and speed values exist. As I noted, the shock waves can be stationary, like these 2 in this example, or moving. Note that although I have represented the location of a shock wave at an instant by a line, the actual change occurs over some small length, since a distance is needed to change speed. The point at which the speed reduction takes place can be approximately noted by the turning on of the brake lights of the vehicles. An observer will see that this point moves upstream as traffic continues to approach the vicinity of the bottleneck, indicating an upstream movement of the point at which flow and density change. You can try to observe this on an approach of a busy intersection. The phenomenon discussed occurs on every cycle where a queue grows and then dissipates when the signal turns green. We will discuss more about this later in the class. In order to solve shockwave problems, we need an equation that yields the shockwave speed as a function of the flow and density of the two traffic states on each side of the shock wave. We are now going to derive such an equation. Suppose that we label the two traffic states 1 and 2 as shown in this time-space diagram. For simplicity, we're assuming each vehicle on a traffic state travels at the same speed, although this assumption can be relaxed without altering the equation we're going to derive. Now, let's consider a rectangular area defined over a segment of length delta L and an interval delta T. We label the number of vehicles entering or leaving the rectangular area as N1, M1, N2, and M2. For example, N1 is the number of vehicles in state 1 entering the rectangular area over the delta T interval. It's in this example it would be 1, 2, 3, 4, 5, and 6. M1 is the number of vehicles in state 1 leaving the rectangular area over the segment of length delta L. In this example, we will have only 2 of these vehicles. Similarly, M2 is the number of vehicles entering the rectangular area over the length delta L. And in this example, it would be 1, 2, 3, and 4. And N2 is the number of vehicles leaving the rectangular area over the interval delta T, and in this example would be 8, if we count the number of vehicles we have here. Note that we use the subindex 1 or 2 depending on the state. So for N and M, we use here the subindex 2 because this corresponds to state 2, and these conditions correspond to state 1, and that's why we use the subindex 1 for N1 and M1. Now, since we are neither creating nor destroying vehicles, assuming there are no driveways in this area, time-space area, the sum of vehicles entering the area minus the sum of vehicles leaving the area must be equal to 0. Or in other words, M2, these are entering vehicles, minus N2 because these are leaving, minus M1 because vehicles are leaving through here, plus N1 has to be equal to 0. If we divide by the product of delta L and delta T, we are going to obtain this expression. And then if we recognize that M2 divided by delta L is nothing more than the density, remember M2 we have it here, and we are dividing by this length, so it's a measurement at an instant of time taken over a certain length, and that's nothing more than the density of state 2. We also see that M1 divided by delta L, again here we have M1 on the state 1 side, that would be the density corresponding to state 1. Similarly, if we look at N1 divided by delta T, that will give us the flow for state 1, and N2 over delta T will give us the flow for state 2. So replacing these quantities and rearranging, moving these elements to the other side, we obtain that K2 minus K1 divided by delta T is equal to Q2 minus Q1 divided by delta T, and that can be further rearranged as delta L over delta T equal to Q2 minus Q1 over K2 minus K1. And we label that as the speed of a shock wave, since it clearly represents the speed at which the location of the interface is moving in the time-space diagram. This equation is the shock wave equation, and it is fundamental for solving shock wave problems. Note that it's simply the difference in flows divided by the difference in densities. It does not matter which state you label as 1 or 2 as long as you do it consistently in the numerator and the denominator. It's important to know that the sign of the speed is important because it indicates whether the wave is moving forward or downstream, as in this example, or backwards or upstream when it's negative. Let's now look at an application with an example taken from chapter 3 of the book Transportation Engineering and Planning by Papakostas and Provedores. Consider a traffic stream that is initially in state 1 as shown in the following flow density diagram. Based on the calibrated diagram, state 1 corresponds to a flow Q1 of 1000 vehicles per day, a density or concentration K1 of 25 vehicles per mile, and a space mean speed of 40 miles per hour. The density corresponds to a spacing of 211 feet. The first two, Q1 and K1, are shown explicitly in the diagram, whereas the speed of state 1 is simple, the slope of the line from the origin to the point corresponding to state 1. As we continue with this example, other quantities will be provided for other states. But it's important to understand that those are also points on the calibrated flow density diagram. For ease of explanation, the equation of the flow density diagram is not presented in this example. However, for most problems, you will be given an equation relating either flow to density or flow to speed or speed to density, which together with the fundamental traffic flow relationship Q equal Ku will allow you to compute two of these quantities or these variables, knowing the third one. Now assume that a track in the stream decides to slow down to 10 miles per hour, and a situation that will cause something like this would be, for example, a very steep grade where the track is forced to slow down because of its weight to horsepower ratio. If passing is not permitted, the vehicles behind the track will also need to slow down at some point to match the track speed. With time, a moving platoon of vehicles traveling at 10 miles per hour will grow behind the track. At any instant, the last vehicle to join the platoon will be traveling at 10 miles per hour, but further upstream, vehicles will continue to approach the platoon at the original conditions. Let us see what happens graphically. The red lines in this time-space diagram represent the trajectories of vehicles on state 1. The headways and spacing S represent respectively the flow and density of state 1 shown in the flow density relationship or the flow density diagram. Note that on the flow density diagram or the QK diagram, the slope of the line that joins the origin to the point with coordinates K1, Q1 is U1 because of the fundamental flow relationship Q equal Ku. Now, the track slows down to the speed corresponding to state 2. Thus, the trajectory of the track is represented by the last red line until the track slows down, and by the black line after that. Since vehicles behind the track will be forced to travel at that speed, a traffic state with an average speed of 10 miles per hour forms behind the track. Given that traffic on this highway follows this traffic flow relationship, the traffic conditions behind the track correspond to state 2 in the QK diagram. Note that you can always pick the scales of the drawings so that the lines representing the same speeds in both diagrams are parallel. Looking back at the time-space diagram, we note the first vehicle behind the track slows down to the speed of the track. Then the second vehicle does the same a little later, then the third does the same, and so on. Notice how the interface between the two states is defined by the dashed blue line and that it is moving at a given speed in the time-space domain. As derived earlier, the speed of the shock wave between states 1 and 2 is given by Q2 minus Q1 divided by K2 minus K1, or delta Q divided by delta K. And again, I repeat, you could have written this as Q1 minus Q2 divided by K1 minus K2, and you would get exactly the same result. This equation in the QK diagram is given by the slope of the solid blue line joining states 1 and 2. As defined earlier, a shock wave exists whenever traffic streams of varying conditions meet. Consequently, other shock waves can be identified in these diagrams by noting that in front of a track, a new state with zero flow and zero density exists. These are identified by these numbers 3 in both diagrams, so we can see here some where this state exists, where we have essentially no vehicles, no density, no flow, and therefore in the QK diagram that appears as Q0 and K0. We see we have state 2 has an interface with state 3. And obviously there needs to be a shock wave in between, and in this particular case, if we look at the QK diagram, we just need to identify the two states. So state 2 here and state 3 there, and therefore the line, which is given here by this black line, joining the two states, will give us, the slope of that line will give us the speed of the shock wave between states 2 and 3. That happens to be, in this particular case, the line that we define for 10 miles per hour, because in this case, that shock wave corresponds or coincides with the trajectory of a track. So this black line here in the time space diagram and the black line in the QK diagram represents the speed of the shock wave between states 2 and 3, as well as the speed of a track in this particular case. This is just something very particular for this example. In general, the speed of a shock wave does not coincide necessarily with the speed of any. Note that we also have an interface between state 1 and state 3. This is given by the continuation of the line of the trajectory that the track would have had if it had not slowed down. So by this line here. So that's the interface between states 1 and 3, and in general, when we want to get the speed of a shock wave, which is that interface, we have to look at the QK diagram and identify the two states. So in this case, we identify again state 1 here and state 3 here, and the line that joins them, the slope of that line, will give us the speed. Now, in this particular case, again, because state 3 is very particular in the sense that it has flow 0 and density 0, that coincides with the speed corresponding to state 1, because in both cases we have a line joining the origin to that particular state. So the speed of the shock wave between states 1 and 3 happen to be the speed of the vehicles traveling in state 1 as well. Now we're going to continue with one of the problems in Papacosas and Prevedores, and it says, determine the magnitude and direction of the speeds of the two shock waves AA and BB, and determine the rate at which the platoon is growing behind the track. Those lines AA, or the shock waves AA and BB, are given in figure 361 in the text, which is basically the same thing we have here for our case. AA is this line, and BB is this other line. Okay. So AA corresponds to the front of the moving platoon, and BB corresponds to the rear of the moving platoon, which is when vehicles cross this line, they suddenly adopt the speed of the track. If you read the problem in the book, the conditions for Q2 and K2 are given as Q2 equal 1200 vehicles per hour and K2 equal 120 vehicles per mile, which correspond to U2 equal 10 miles per hour of the track. And again, typically could have given you just, or they could have given you just the 10 miles per hour of speed of the track and tell you about a relationship, a QK relationship, and that would have been enough for you to figure out what Q2 and K2. In this case, those values are given, so you don't have to worry about how to compute them. For the free flow conditions, basically we have no traffic, zero traffic, and of course we have zero density, so Q3 equals 0 and K3 equals 0. So having identified the two flow states, then computing the speed of the shock wave is very simple. It's just a matter of substituting values. So the speed of the shock wave for line AA, as noted in the problem in the book of Papacostas and Prevedoros, or for our case, for example, is between states 2 and 3. It's just simply Q3 minus Q2 divided by K3 minus K2, and we just need to substitute values. And I put the units in there so you can actually see that this will necessarily have to give you the right units of, in this case, miles per hour. So when we make the calculation, we get that the speed of the shock wave happens to be the speed of the track, and it's 10 miles per hour. So we have mentioned that before, but now we have the calculation that shows us that that's the case. To obtain the speed of the shock wave at the rear of a platoon or between states 1 and 2, so let's go back in there, between states 1 and 2, so the speed of this shock wave in between state 1 and state 2. Again, we have to identify the two states in our QK diagram, 1 and 2. We have to identify what the values of those states are. So the approach conditions, that was how we started the problem, were given as 1,000 vehicles per hour and Q1 1,000 vehicles per hour and K1 equal 25 vehicles per mile. And we were also told that the platoon conditions Q2 were the same that we just had in the previous part of this problem, which is Q2 equal 1,200 vehicles per hour and K2 equal 120 vehicles per mile. So again, it's just a matter of writing the right equation for the speed of the shock wave for shock wave BB, which happens to be the shock wave between states 1 and 2. That's why I use those sub-indices. It's just simply Q2 minus Q1 over K2 minus K1. And again, if we substitute the values we have here, we end up with a speed of 2.1 miles per hour. Again, this speed is positive, meaning that the shock wave is moving downstream or forward. With these speeds, with the speed of the two shock waves, we can now answer at which rate the platoon is growing behind the track. That was the original question we had in the previous problem. Okay. So specifically, the rate of growth of a platoon is given by the relative speed between the two. 10 miles minus 2.1 miles per hour equals 7.9 miles per hour. Obviously, in this case, since the two speeds are positive, the relative speed would be their difference. So notice that sometimes when we get one wave moving forward and the other one moving backwards, so when you subtract that negative number, so in essence you end up adding them up. In these slides we see again where more or less what we have done so far. Basically we have determined the speed of this shock wave, which is the front of a platoon, and the speed of this shock wave, which is the rear of a platoon. And what this graph shows us is that over time the platoon grows in size. So at this point in time, for example, this is the estimated length of a platoon. At this other point in time, t prime, this would be from here to here, would be the estimated length, and so on. After a while, this keeps growing and more vehicles are adding to the platoon. Of course, in typical situations, you will not see a graph with so many lines. Typically, what you will see would be something like this. We don't draw vehicle trajectories, individual vehicle trajectories, although it's very useful for you to be able to draw one or two or a few, just to make sense of what you're doing when solving this type of problem, so you don't lose sight of where you're going with the problem. Okay? So we will be alternating in this class between, when I present the information, I will put some individual vehicle trajectories so you understand what's happening in the different traffic states. But to solve problems, typically they kind of distract a little bit of from where you're going. So typically this type of diagram would be more useful for solving the problem with just a couple or a few lines added to it. This slide presents a few pointers which are important. Please do not confuse the speed of a shock wave with the speed of any vehicle in the traffic stream. Sometimes, like we have seen in this particular example we're dealing with, the speed of a shock wave coincides with the speed of the track, which actually represents one traffic state, is the traffic state corresponding to congested conditions. And another shock wave, the speed of another shock wave coincided with the speed corresponding to traffic state 1. Again, this is a very particular example. In general, the speed of a shock wave does not need to correspond to any traffic state. As in this example, it may happen that the speed of a shock wave is equal to the speed of a traffic stream, but again, this is only a particular case. It's not true in general. It is of interest to note also that although the track forced the traffic stream to slow down, the traffic flow increased from 1,000 to 1,200 vehicles per hour, a situation that frustrated drivers would be unaware of. We slowed down traffic and the traffic flow rate increased from 1,000 to 1,200 vehicles per hour. And what this points out is that in certain cases, slowing traffic via a traffic control system may be a good way of increasing flow. In this particular example, we don't gain anything because we are not using the area with the state 3 for anything else. But because of the track slowing down, traffic in this state that before had 1,000 vehicles per hour now is flowing over here at 1,200 vehicles per hour. But it's flowing at a lower speed with much higher density. Now, we don't gain anything from that because in this area we are not using this for anything else. But imagine an intersection where if we, instead of having a track slowing down, the first vehicle has to stop because of a traffic light. In that particular situation, the conditions expressed in a time-space diagram, let's put time and space. So at some point in time, the first vehicle gets stopped altogether, and then instead of having the back of a platoon moving forward, like in this example, in that situation the back of a platoon will always move backwards. Okay? So this would be our state 1 here, initial conditions, this would be state 1. In here we'll have then state 2, and this will be state 3. This is how this same diagram would look like in the case of an intersection. In this situation, this empty space 3 here can now be used to move cross-street traffic. So the system can gain a lot by controlling traffic in one direction to move traffic in a conflicting direction. Let's continue with the next example in the book of Papacostas and Proveedores, which is a continuation of the previous problem. It says, assume that the track exited the traffic stream 10 minutes after slowing down. Vehicles at the front of a platoon were then released to a speed of 20 miles per hour and a concentration of 70 vehicles per mile. Then we are also asked to compute the amount of time it took the 10 miles per hour platoon to disappear. Remember that the platoon is traveling at the same speed at which the track had slowed down, and that platoon is growing over time. So let's try to understand what this problem is about. Basically, this situation is saying that the time from the moment the track slowed down until it was able to accelerate or left the traffic stream, it took 10 minutes. At that point in time, the platoon is now of a certain length that we don't know but we can compute. And then we're told that after that, then after the track accelerates, we're told what the conditions are going to be. And we were told a state with 20 miles per hour and 70 vehicles per mile. Typically, when that happens, when you have a platoon and then people are able to move faster, typically that would be represented by the capacity conditions. So the 70 vehicles per mile corresponds to the density at capacity. This would be the 70 vehicles per mile. And the speed, 20 miles per hour, would be given by this, the slope of that line. Remember, in this diagram, always, when we draw a straight line from the origin and to a point in the diagram, then the speed is determined by the slope of the line joining the origin and that point. So this would be 20 miles per hour. And of course, if you multiply speed and density, that will give us the flow. So even though we are not told what that flow is, but that flow would be, I'm going to call it Q4 equals 14 vehicles per hour. So this would be K4, and this would be U4, which corresponds to this state that would be state 4. So we will need to figure out which new shock waves will be formed, and then at what point the platoon that has achieved this length now will disappear. Let's start with the easiest part, which is figuring out what's the length right now of this platoon. An easy way to compute the length of a platoon after a given period of time is to realize that the platoon will be growing at the rate at which these two shock waves, this one representing the front of a platoon and this one representing the rear of a platoon, diverge, which is given by the relative speed of the two shock waves. We already computed this value as 7.9 miles per hour, and thus, to get the length of a platoon after 10 minutes, we just need to multiply the relative speed by the 10 minutes expressed in hours to make the units consistent. When we do this, we obtain that the platoon length is about 1.32 miles. If we were asked about the approximate number of vehicles in the platoon, all we need to do is to multiply that length by the corresponding density, which in this case is the density of state 2, which represents the platoon conditions, and is equal to 120 vehicles per mile. When we do that, we obtain that the platoon consists of about 158 vehicles. This slide shows graphically what we have just done. We have looked at the relative speed between these two shock waves, and when multiply the relative speed by the interval of time, 10 minutes, it gives us this length. If you're not convinced about this approach or you cannot visualize it, there is another easy way to see it, and it's simply to look at the length we have just computed as the difference between the length between these points, which is simply obtained from the speed of a shock wave in the front of the platoon, and subtract from it this other length, which is related to the speed of the rear of the platoon. So we can say that the length of a platoon after 10 minutes, that would be the 1.32 miles per hour you see in the graph, is equal to the speed of the shock wave between states 2 and 3, which is 10 miles per hour, multiplied by the interval of time, let's call it delta t, minus the speed of the shock wave at the rear of the platoon, which is between states 1 and 2, multiplied by the same delta t. So basically we come up with the same conclusion. Is the difference, is the relative difference between the two speeds of the shock waves multiplied by delta t, which is exactly what we did before. But this is a more graphical way of seeing the same result. Now, let's remember what the question that we have to answer is. Remember that what we need to answer is this. The amount of time it took the 10 miles per hour platoon to disappear. So we have computed so far that after 10 minutes the platoon has grown, but now we have to look at how that platoon is going to disappear after we take the slow track out of the equation. Note that after the track exits the traffic stream, another shock wave develops between the platoon conditions represented by state 2 and a new condition, which we are going to call the release conditions, which as indicated earlier correspond to the capacity of the section, and this is going to be shown as state 4 in the QK diagram. This is logical, since before traffic was forced to follow the track, but now, since they can move faster, drivers could leave at the maximum possible flow rate, which is the capacity. Note that now we have a new shock wave between states 2 and 4 that define the front of a platoon. Before, in the first 10 minutes, the front of a platoon was given by this line, which was coincident with the trajectory of the track. But now the track is gone, and then once we take the track out, the vehicle behind will become the leader of a platoon until it changes state conditions from state 2 to state 4, and then the next car will be the platoon leader, and so on. To visualize this, let me try to draw this manually. So I'm going to try to draw the vehicle trajectories, so and also so you can see how this is basically how you would do it. So vehicles in state 1 were traveling with a speed corresponding to this slope here. So all I need to do to draw those vehicle trajectories is draw parallel lines to that line corresponding to state 1. So if I look at another vehicle behind the track, so that vehicle was traveling in state 1. Then at that point, when it reaches the rear of the platoon, now I have to look at the speed corresponding to state 2. So I have to look at this slope will give me the speed for vehicles in state 2. And so I will draw a parallel line to that line that goes from 3 to 2. So a parallel line will be something like this. So this would be the trajectory of the car immediately behind the track. And now that car, when it reaches the front of a platoon, it will move to a state 4. And for that, I would need to draw a line parallel to this line that goes from the origin to state 4. And so if I draw a line parallel to that, it would have, we'll try to do my best in here, it would be something like that. And the next vehicle will do exactly the same thing. The next vehicle will do the same thing, and so on. This is basically how you interpret. Notice that here state 1 is different from state 4, as we see in this other graph, in the QK graph. The slope of the line for state 1 here is higher than for state 4. So even though we are releasing people at the maximum capacity, at the maximum rate, it's still, the speed still has not recovered. In practice, what will happen, let's say we consider also that the track, let's assume the track accelerated at this speed just to make the graph complete. What would happen is that once you have vehicles can accelerate, over time they will not follow this path, but they will accelerate until this line becomes parallel to the original condition. So after a while, traffic will return to the conditions, but that takes a while, and that's why we ignore in these problems that we are looking at what's going to happen in a short distance, relatively short distance of the road. Okay, so this is just to give you an idea of what we are doing. What does this line over here means? Okay, so it's not a physical thing, it's just the location of the leader of a platoon is changing, and that leader is changing over time, right? So at this point in time, this vehicle was the leader, and then the following vehicle was the leader, and so on. So the front of the platoon is changing. Now we see that the shock wave defining the front of a platoon, this shock wave, is traveling backwards and is going to meet the shock wave representing the rear of the platoon that is still moving forward. So what's going to happen at some point, these two shock waves are going to meet. And at that point, the platoon would have disappeared. So what we need to find is this time that we have it here already. We have the answer, but later we're going to make the calculations. That's the time that is unknown to us. But the solution to this problem is relatively simple, because now if we look at this, we know that this length is 1.32 miles. We solved already for that. And then if we realize, well, these two shock waves are traveling at a relative speed, if we figure out that relative speed, we do exactly the same thing that we did before, which is, okay, how long it would take, how long this time would be. Okay, so before we knew the time and we multiply by relative speed to get the length. Now we do the opposite. We have the length and we have the relative speed, so if we divide that length by the relative speed, we will get this time over here, which is unknown. So now we're going to make the computations, but this is the reasoning behind. And the most important things about these problems is understanding the problem. It's figuring out when a shock wave is created or not. Now let's make the calculations. As we mentioned before, after the track exited the traffic stream, another shock wave developed between the platoon conditions and the release conditions, that is between the states 2 and 4 in the QK plot. So it's just a matter of identifying the conditions for these two states. Remember that the flow for state 4 was equal to 1400 vehicles per hour, the flow for state 2 was equal to 1200 vehicles per hour, and the densities were 70 and 120 vehicles per mile for states 4 and 2 respectively. So when we plug in the values, we compute the ratio, we obtain that the speed of a shock wave between states 2 and 4, which represents the front of the platoon after the first 10 minutes of this problem, it's minus 4 miles per hour. The negative sign coincides with what we mentioned before, that the speed now is traveling backwards or upstream. Now, the rear of the platoon is still moving downstream or forward at 2.1 miles per hour. So now the relative speed between the two waves is 2.1 minus the negative 4, which ends up being 6.1 miles per hour. Make sure you don't mess up this step, because your solution can change dramatically if you compute that relative speed wrongly. And with that, since we know that the length of a platoon after 10 minutes was 1.32 miles, then we divide by this relative speed to get a value for the platoon dissipation of 2.116 hours or 30 minutes. So that is, it took 30 minutes after the track departure for the platoon to dissipate totally. This slide shows several things we have been discussing and a few more that we are going to discuss more. So far we have said we have traffic in state 1. At some point we have a track that hits either a steep grade, or for whatever reason we have a track entering the highway at 10 miles per hour. So that track slows down everybody, so every vehicle has to join a platoon that is forming in this area here, region 2, and the rear of the platoon then was given by this shock wave traveling forward at 2.1 miles per hour. This is the front of the platoon during the first 10 minutes, traveling at 10 miles per hour, but after 10 minutes, when the track either accelerates or leaves, then the front of the platoon starts traveling backwards, and we determine that this length here is 13 minutes. So obviously the graph is not up to scale, but that's what we have described so far. We also mentioned that this line here represented another shock wave between states 1 and state 3. And you can see that the slope of that line, we could get it from joining states 1 and 3 in the QK diagram. Similarly, this shock wave was determined by the two states that is separating, is between states 2 and 3. So we can see that if we look at states 2 and 3, that's the slope of this shock wave, which happens to coincide with the speed of the track of 10 miles per hour. This one, which is the shock wave between states 2 and 1, again we have to look at states 2 and 1, and we see that that blue line happens to be parallel to this blue line. Now, notice that after the track leaves or the track accelerates, we have a new shock wave. Now, this new shock wave is between state 3 and 4. Remember, every time we have two different states, there has to be a shock wave in between them. And in this case, between 3 and 4, there needs to be another shock wave. So we look at, in the QK diagram, at states 3 and 4, and we can easily determine what that speed is going to be. Again, because for state 3, Q is equal to 0 and K is equal to 0, the speed of that shock wave coincides with the speed of the traffic condition corresponding to state 4, which was given to us earlier as 20 miles per hour. So that's why we draw that line corresponding with a slope of 20 miles per hour. Finally, now if you look at your graph, in here state 2 disappears. So now at this point we have to have an interface between states 1 and 4. So one more time, if we look at our QK diagram, we locate states 1 and 4, we draw a line, and therefore the speed of that shock wave has to be parallel to that line. That happens to be 8.9 miles per hour if you plug the values for state 4 and 1. And we will see this. We will see how to do this shortly. There are a couple of two more things here. Notice that you can easily determine how far the rear of the platoon travel until the platoon dissipates by knowing this speed and knowing the time, because now we know this time was 23 minutes since the time the track entered the highway until the platoon dissipated. We solved for that before. Similarly, since we know this speed, this slope, and we know the duration, which was 10 minutes, we can easily compute this length here. Okay. As I just indicated, the point where the platoon disappeared was 0.8 miles from the initial point, even though the front of the platoon had been as far as 1.67 miles ahead of the location where the track slowed down. And this is important because typically the congestion relief time is longer than the duration of the flow disruption. And this is why freeway accidents during peak periods tend to create very long-lasting jams. Now, the next problem is related to the last thing I discussed in the previous slide, which is about the last shock wave between states 1 and 4. So this problem says determine the speed of a shock wave that commences at the instant when the 10 miles per hour platoon was totally eliminated. And that shock wave is, as I mentioned a few minutes ago, a shock wave separating states 1 and 4. Okay? So therefore the speed of a shock wave is just a matter of identifying those two states. These values are given to us. For state 4, 1400 vehicles per hour, and for state 1, the flow is 1000 vehicles per hour, and the densities for state 4 and state 1 are 70 and 25 respectively. So after we plug in the values, we obtain that the speed of a shock wave now it's a forward moving wave, or a wave traveling downstream at 8.9 miles per hour. This problem, this whole lecture is representative of a type of problems we are going to cover in the class, particularly the first part about determining the length of the moving platoon or the time until the queue dissipates. So that's basically what we're going to cover in the class. Let me just cover for completeness what happens on freeways. I try not to include this in the class for problems because it's a little bit more complex. But so we're going to describe the problem that we with which I introduced the subject at the beginning of this lecture. So let's consider that situation where we have a freeway with traffic flowing relatively freely, and so we have a traffic state with a flow and a density in the uncongested flow regime, part of a QK diagram. And all of a sudden we have an accident that blocks two lanes. So a few things happen here. The first one is that on the accident itself, traffic is going to filter through that lane at a flow that depends on the capacity of the lane. So you have to recognize that now in this area, the area of the accident, we have only one lane. So the traffic flow relation, the QK relationship of the one lane is different from the QK relationship of the three lanes we have approaching and the three lanes we have afterwards. So what happens is that now we have to look at things between these two different QK relationships for the two different segments of a highway. So this is complex. So the reality, you have to recognize that even though the demand for traffic flow on this segment of highway was this flow, this high, because of the accident, the cars are going to be able to pass that point at the maximum flow corresponding to the one lane segment at this point. Okay? So what happens is that that's what's going to happen here. But immediately before and immediately after we have a three lane section. So we will have basically in here the flow in this congested part would be exactly the same as the flow we have on the one lane, right? So people here will will pass that point at the maximum rate they can, and the maximum rate they can is this one. So we will have a horizontal line because the flow on the freeway immediately upstream of the accident would be what can pass through the accident. So we are forcing the flow to be this much. So now what we have is the approach conditions here are where correspond to these blue cars, and now we have the congested conditions here, or the platoon conditions, and in this case it would be a queue because it's pretty much stationary. The front of the platoon now is stationary, so typically I would call this a queue. So it's a different state. So these are the two states that we need to identify for this shock wave, which would be traveling backwards, as you see when we put this line. So this line is telling me that at what speed, the slope of this line is telling me at what speed this shock wave will be traveling backwards in time. Now, for people filtering here, immediately after the accident, the flow rate would be essentially the same as what we have at the accident. So we will have, this other shock wave between this state, orange, and that state, and that shock wave is stationary. That's why this line will not be moving because it corresponds with it has a slope of 0 joining the two states. The same thing happened with this one at the scene of the accident and the congested condition. That's a horizontal line, so that's another shock wave, but it's stationary, it's not moving. Okay? As I mentioned before, the Q will be growing backwards, which is as represented by this longer Q. Now, at some point, the accident is clear, and this is what's going to happen. When the accident is clear, that state at the scene of the accident disappears, so we took out the density flow relationship, and now we still have an interface between the approach conditions and the platoon conditions, or the, before it was a queue, but now I want to call it a platoon. You will see why shortly. That is still the speed of that shock wave is still determined by those two states. So that shock wave is still traveling backwards in time. That shock wave is still traveling backwards or upstream, even though the accident has already been dissipated. On the other hand, the people that before were filtering through the accident, once you take the accident out, they try to move at the fastest rate they can. And the fastest rate they can is the capacity of the QK relationship. This is the maximum flow rate. So now we have another shock wave between the congested conditions and these capacity conditions. So this is another wave that will also be traveling backwards in time. But notice that the speed at which this shock wave travels backwards in absolute value, it's larger than the speed of this shock wave also traveling backwards. So I'm looking at the two shock waves in absolute values. So that means that if this shock wave travels faster than this, backwards, at some point the Q will dissipate as well. Finally, we have people traveling at capacity conditions with people traveling freely in front of them. Obviously, you don't want to be traveling at capacity conditions, so the guys at the front will travel freely. So we have that shock wave, which is not that very important for our discussion, but just for completeness, it's just a matter of joining these two states. As I mentioned before, this shock wave travels faster than this backward, and therefore at some point these shock waves will meet. At that point, this congested state will not exist anymore, and what it could happen then is that we will have an interface between this state and that state. This is what is shown here, and we will have a new shock wave traveling now forward very quickly, joining the two states. So we will have another shock wave traveling forward, and all these cars, supposedly according to this theory, these shock waves will never meet, but you know, these things will move forward. At some point people will leave the freeway and we will have the normal conditions on the highway once again. And with that, that's all I wanted to say, just to give you an idea of how this analysis can be used for how this shockwave tool can be used for analysis of what happened on freeways. There's simulation software, microscopic simulation software, that actually use these techniques to determine what happens on freeways. We will not be using that in this class. The theory can also be used to figure out delays. We have not talked about that, but it's relatively complex. The most important thing for us is to be able to visualize what you can do if you close because of construction, what could be the consequences. So I think that as engineers, you have to be aware of the things that you, or being able to quantify it very grossly, what effects your actions can have.